So now at last we are ready to define the notion of the satisfaction of a first order formula in a structure, and this will have to be relative to a variable assignment or under a variable assignment. So we will use this notation. So structure, comma, variable assignment. Let's use S for that to be consistent. A variable assignment S, and then the double semantic turnstile for the formula. So this is going to mean that in structure M, relative to the variable assignment S, phi is satisfied. All right, so we need to define this, you would have guessed it, inductively on the structure of phi. So what could phi be? So we need to follow the inductive or recursive definition of the set of first order formulas, and for each of those cases, write down the clause when a formula of that form or with that main connective will be true in a structure under a particular variable assignment. All right, so the first option is when phi is the falsum, right? And so, well, simply, as you would expect, the falsum is supposed to be something that is always false, so it will never be the case that a structure under relative to any variable assignment satisfies the falsum. That simply doesn't happen. And as one would expect also, the verum or the top, that's always satisfied. We don't even need to ask what the structure is and what the variable assignment is. That thing is always true in every structure relative to every truth assignment. Next, we need to look at atomic formulas because they come next in the definition of formulas, in the recursive definition of formulas. So the first way an atomic formula could have looked is it was an n-ary predicate symbol applied to n terms as arguments. All right, so this is going to be the case. Well, I mean, intuitively, we want to say that, well, the objects denoted by these n terms stand in the relation, the n-ary relation, which gets denoted by R in this structure. All right, so this is going to be the case if and only if now. So now I need to say, what are the values of these terms? So we know how to calculate the value in the structure relative or under the assignment S of each of these terms. The first one up to the nth one. Well, if this n tuple of objects or elements of the domain of the structure, these are n elements in the domain of the structure, if they stand in the n-ary relation interpreting the n-ary predicate symbol M. So basically, if subject to the interpretation of the language, if the objects denoted by the terms stand in that relation. That's what we would want and expect. So this is the first way that an atomic formula could look. The second way that an atomic formula could look is it could be the equality between two terms, T1 equal to T2. Well, intuitively, we want that to be true if and only if the values of those two terms in the structure relative to assignment S were the same. Yes, that is indeed what we would want, and we simply specify it to be that. The value of T1 in structure M relative to assignment S is equal to the value of term T2 in structure M relative to assignment S. All right, so those are the base cases. We've covered the falsum, the verum, the atomic formulas. So now we need to start looking at the propositional connective. So if my formula is the negation of some formula, if it's not psi, well, here our intuitions from propositional logic come in. Well, I'd want this guy to be true, the negation, if and only if in that same structure, under that same variable assignment, the psi, the argument of the negation, is false. So the negation is true, the negation of a formula is true in a structure relative to an assignment, if and only if the negated formula is false or not true in the structure relative to that assignment. All right, next up is conjunction. So if my formula is a conjunction, say between psi and chi, that's going to be true as expected, if and only if in the same structure, under the same, or relative to the same assignment, both psi and chi are true, right? The next is when my formula is a disjunction. So the disjunction of psi and chi is going to be true in structure M relative to assignment S, if and only if psi is true or chi is true in that same structure under the same assignment. And then we come to the implication. So this is going to be true. Psi implies chi. Well, this is as we would expect from what we learned in propositional logic. Either we need to have the antecedent false in that structure under that assignment, or we need to have the consequent true in that structure relative to that assignment. And lastly, the by implication is going to be true if and only if, well, the truth values in that structure, or they're both satisfied, or both not satisfied. So if and only if we have both that psi is satisfied and chi is satisfied, both this or both is actually redundant. Both of them are not satisfied. All right, so much for atomic formulas and formulas which have propositional connectives as their main connectives. Now we come to the really interesting case, the thing which really is characteristic of first order logic, and that of course is the quantifiers. So when is a universal quantifier true or satisfied in a structure under an assignment? So for all x psi. All right, so let's think of what this means intuitively. It says for every object in the domain of my structure, psi is going to be true. So now x is a variable. So basically this says for every way that I can interpret the x, for every value in the domain that I can assign to x, psi needs to be true under that assignment. But of course, there might now be other variables occurring in psi, and their values still need to be determined by S, right? So we're not going to fiddle with the values of other variables in psi, only possibly with X. So, and this is where the notion of an X variant that we defined on the previous slide comes in. So this is going to be the case if and only if M in the structure relative to S prime, psi is satisfied, and this is for all X variants S prime of S. So however you could change the value of X, psi will still have to be true. Other variables, now remember this is an x variant, so S prime can disagree from S in at most the value of x. So it cannot change any other variable's values, only x. But so basically what we're doing is here we are running through all possible values in the domain, all possible elements of the domain, and we are assigning them one after the other to x, and then we're seeing under that assignment is psi true. And if that's the case, then for all x psi is satisfied in this structure under or relative to the assignment S. So all that remains now is the existential quantifier, right? And so you can guess how we will define that. We're going to say, well, this is going to be the case if and only if under some S prime, psi is satisfied for. So for some S prime, which is an X variant of S. And this makes sense given our intuition about what an existentially quantified formula should be saying. This says there is some element of the domain of the structure which I can assign to X, and then under that assignment, psi needs to be true. So we need to go and look and see, can I find some X, value for X, which is going to make psi true. But of course, all other variables need to hold their values under S. So I can only look at S primes which are X variants of S. Assignments which disagree or differ from S in at most the value of X.